Human intelligence is not a static capability, but a continuous experience-driven process shaped by reward-guided trial and error. Herbert Simon's influential work in artificial intelligence characterizes human behavior as fundamentally reward-driven, where biological intelligence emerges from relatively simple mechanisms responding to incentives. Although human cognition appears extraordinarily complex, this complexity arises from repeated interactions with a rich and dynamic environment. Artificial intelligence draws inspiration from this principle, aiming to replicate intelligent behavior by modeling how simple reward-based learning strategies can give rise to sophisticated decision-making over time. Reinforcement learning embodies this biological inspiration within machine learning. It is a framework in which an agent interacts with an environment, observes states, takes actions, and receives rewards that guide future behavior. The objective is to maximize the expected cumulative reward over time, enabling the agent to learn optimal policies through experience rather than explicit instruction. This paradigm has enabled the creation of intelligent systems capable of adapting to complex and uncertain environments, including game-playing algorithms, autonomous vehicles, and robotic control systems. Recent breakthroughs in reinforcement learning have been driven by the integration of deep neural networks, giving rise to deep reinforcement learning. These methods allow agents to process high-dimensional sensory inputs such as images, audio, or raw sensor data while simultaneously learning decision policies. A prominent example is DeepMind's AlphaZero, which achieves superhuman performance in chess, shogi, and Go using self-play alone, without reliance on human expert data. Beyond outperforming humans, these systems have reshaped strategic thinking in these games, demonstrating how reinforcement learning can uncover novel and highly effective strategies. Reinforcement learning encompasses a broad spectrum of methods and algorithmic frameworks. Stateless approaches, such as multi-armed bandits, focus on reward optimization without explicit state modeling. More advanced methods incorporate state representations and value estimation through techniques such as Monte Carlo sampling, temporal difference learning, and bootstrapping. Algorithms like Q-learning and deep Q networks use function approximators to handle large or continuous state spaces, while policy gradient and actor critic methods directly optimize decision policies. These approaches can be adapted to on-policy or off-policy learning, discrete or continuous action spaces, and planning strategies such as Monte Carlo tree search. The applications of reinforcement learning extend far beyond games. In robotics, agents learn locomotion, manipulation, and control skills through interaction and feedback. In autonomous driving, reinforcement learning contributes to decision-making processes that reduce human error. In natural language processing, it supports conversational systems and dialogue management. Additionally, reinforcement learning has been applied to neural architecture search, automating the design of deep learning models themselves. Despite its successes, reinforcement learning presents significant challenges, particularly in terms of safety, stability, and interpretability. Reward functions often simplify complex real-world objectives, which can lead to unintended behaviors if not carefully designed. Exploration strategies may expose systems to risky actions, especially in safety-critical environments. As a result, responsible deployment of reinforcement learning systems requires careful reward modeling, robust evaluation, and the integration of safety constraints. Advanced topics in deep learning often extend beyond foundational architectures and require independent treatment due to their conceptual depth and computational complexity. These topics aim to enhance learning efficiency, adaptability, and generalization by drawing inspiration from human cognition, memory, and competition-driven learning processes. One key concept is attention modeling, which is motivated by the human ability to selectively focus on relevant information while ignoring irrelevant stimuli. In neural networks, attention mechanisms enable models to prioritize informative components of the input data, significantly improving performance in tasks such as natural language processing, computer vision, and sequence modeling. By dynamically allocating computational resources, attention-based models achieve greater interpretability and efficiency. Another important area involves neural architectures with selective access to internal memory. These models employ structured addressing mechanisms that control how information is read from and written to memory, enabling logical operations similar to those found in traditional programming. Commonly known as memory networks or neural Turing machines, these architectures overcome the limitations of fixed-length representations and support complex reasoning, algorithmic learning, and long-term dependency modeling. Generative Adversarial Networks, GANs, represent a powerful approach to generative modeling. They consist of two competing networks: a generator that produces synthetic data samples and a discriminator that distinguishes between real and generated data. Through adversarial training, both networks improve simultaneously, ultimately producing outputs that closely resemble real data. GANs have driven major advances in image synthesis, data augmentation, style transfer, and creative artificial intelligence. Classical learning paradigms such as competitive learning remain highly relevant, particularly through models like the Kohonen self-organizing map. Competitive learning supports unsupervised tasks, including clustering, dimensionality reduction, and data compression by allowing neurons to compete for representation, resulting in structured and interpretable feature maps. Human intelligence provides further inspiration for advanced learning strategies. Humans demonstrate remarkable ability to generalize from limited experience, transfer knowledge across tasks, and learn efficiently over time. These capabilities motivate approaches such as meta-learning and learning to learn, where models improve their learning process through experience across multiple tasks. Although powerful, these approaches face challenges related to task diversity, stability, and generalization. Pre-training neural networks on large datasets exemplifies practical learning to learn, enabling models to acquire transferable representations that can be adapted to new tasks with minimal data. In parallel, advances in specialized hardware and neuromorphic computing reflect efforts to integrate learning and computation more closely, inspired by the human brain. These developments include spiking neural networks, low-precision synapses, and energy-efficient architectures. Together, these advanced methods spanning attention mechanisms, memory-augmented networks, generative modeling, competitive learning, and meta-learning represent the forefront of deep learning research. They emphasize adaptability, efficient representation, and the integration of memory and attention as essential components of intelligent systems.